Okay, so we're continuing on. Sorry for the passing period music. We're continuing on, and I realized I made a mistake in what we were doing. The radius is 4 meters on this thing. I accidentally put it as 6. So this is supposed to be a 4, which means the similar triangle we set up is going to be a 4, which means this will be 4/10, which means that'll be 2/5. So we get 2/5 instead of 3/5. The 2/5 get squared. So here we really get volume equals 1/3 pi times 4 over 25 h squared times h. So this one here, the 3 can no longer cancel because I had the wrong. I basically wrote the wrong number down in my problem and carried that through, and that messed a lot of stuff up. So kind of going through, tracing down. We're down to here now. This should be correct. So this volume formula here is not right. We want volume equals, it'll be 1/3 times 4/3 is 4/75 times pi times h cubed. And that should hopefully be the number that we want. So let me just double check, make sure I've got the number that we want correct now. And I think we do. Let's see, it's 1/3 pi r squared. R is, so that's 2/5 instead of that. So yeah, I think we're okay now. So we get d dt, we're going to take the time derivative of both sides. So when we do that, we'll get dv dt over here. And on this side, we'll get 4/75 times pi. And then d dt of h. H is a function of time. So this will be 3h squared times dh dt. So the chain rule applies because the height changes with respect to time. So now we get dv dt equals, the 3 can cancel into the 75. That'll leave me at 25. So you have 4/25 pi times h squared times dh dt. dh dt is what the problem is asking us for. So the problem really wants to know how is the height changing with respect to time. So this dh dt is what we're really trying to find. We're going to plug in the numbers they give us. dv dt is 6. That's the rate the water comes into the tank. 4/25 times pi stays that. H squared, we're asking when the height is 5, so this is going to be 5 squared. And then we get times dh dt. So when we go to solve this, if we have 6 divided by this stuff here, that should be the change in height with respect to time. So I just divided all these numbers across. And we get that this is about equal to 0.477. The units on this would be meters per minute. That is the change in height with respect to time. And so that at 5 meters, that's the rate the water level rises at 5 meters. So this is our answer. Part B on this wanted us to go through and say, Part B says, as time passes, what happens to the rate at which the water level rises? Well, that rate's going to decrease because as the volume goes in, the tank radius increases. So as the height increases, the radius increases, which means when you add that volume of water, it's going to be able to spread out more, and because there's a wider radius, so the height will go up at a slower rate. So we'll say the height rises. I guess water height rises as time increases, slows because the radius of the tank increases as the water height increases. So basically, the higher the water level goes, the bigger the cross-sectional area of the tank is, which means if you're adding the same volume, it will raise the water level at a slower rate because there's a wider area for the new volumes to fit in. Okay, so we're going to move on to final two problems here. So we got example 4. So this one says a spy uses a telescope to track a rocket being launched. Vertically. From a launching pad 6 kilometers away. At a certain moment, the angle between the telescope and the ground is equal to pi over 3 and is changing at a rate of 0.9 radians per minute. So we'll say rad per minute. I want to say, what is the rocket's velocity at that moment? So the picture they give us, got a guy standing there, I guess, has some sort of telescope thing. Pretend it's better than it is. Got a rocket that's going upwards. And this telescope to the rocket, we kind of make a, let's pretend the triangle's better, I guess. They say kind of make a triangle like that. We have the angle theta there. This rocket is height h, and you are a distance x away. Let me try to make this triangle slightly better. The way that they have this kind of designed, or the way that this problem is supposed to be like you're looking basically from here, and you have your theta there, the height there, x is the distance from here to here. And so we basically got a triangle that's a triangle representing the systems, basically h, x, and theta. They told us they told us the rate that the theta is changing. It's 0.9 radians per minute. So we need to come up with an equation that relates x, h, and theta together. And so if we look at this, if the angle's down here, h is the opposite side, x is the adjacent side. So we could say tangent of theta equals opposite, which is h, over adjacent, which is x. And we can probably get what we want from there. The way the problem stated, x doesn't change with time, it's just 6. So I think we can Multiply this x across and say, replace it with a 6 and get 6 tangent theta equals h, because the distance that the person is from the rocket, this horizontal distance of 6, this doesn't change in the problem. The height changes, the angle changes, but the person stays this far away from the vertical launching point the whole time. So here's our equation. We'll take ddt of both sides. Both theta and h change with respect to time. So when we do this, we get 6, which is a constant. Tangent of theta, when you take its derivative, that's going to require the chain rule. So we get secant squared, leave the theta alone, times d theta dt. That equals dh dt, the change in height with respect to time, which is what we're interested in. We're asking what's the rocket's velocity at this moment that the telescope's at this angle with this increase. And that's what this is telling us. dh dt is the rate that the height changes with respect to time, which is the rocket's velocity. So they tell us the angle is pi over 3. And when you're at pi over 3, the rate the angle changes it is 0.9 radians per minute. So we're going to plug pi over 3 in here. And then this right here gets 0.9, replacing it. So we get 6 times secant squared of pi over 3 times 0.9 is the rate that the height changes with respect to time, which is the rocket's velocity. So we get 6 times, let's see, secant is 1 over cosine, so that'd be 1 over cosine of pi over 3 squared times 0.9. And we end up getting 21.6. I got to get the units on it. That's the change in height with respect to time. So that's the rocket's velocity. We were dealing with kilometers is the unit, and it's radians per minute. So minute are the time. So basically what we're going to use here is kilometers is the length, minutes is the time. So the units on this 21.6 are kilometer per minute.